Okay, exponential functions 5.3. Here's the definition of an exponential function. There are a couple of things here that we need to be aware of. The first one is says a has to be a positive real number, so the base has to be positive. And there's a good reason for that. Let's say I had a base of a negative 4. Okay, so if we plug in 0, we get 1. If we plug in 1, we get a negative 4. If you plug in 2, we're back in the positive side. And if you plug in 3, you're back in the negative side. So if you were to look at this like graphically, you're zigzagging here. That's not really a function, at least not what we'd like to see in this case. Okay, so it cannot be a negative base. A cannot be equal to 1. Well, that one's easy. Even easier to show. If it was 1, wouldn't we just always get 1 out of there? So that's not an exponential function. And the last thing is that in this case, here where we have an initial value, c, where does that term come from? Why do we call it an initial value? Well, again, if you raise anything to the power of 0, you just get 1. So if there's a constant here, that's the value that we start with at time 0, so initial value. Okay, let's look at an example of what an exponential function is and what it looks like. So what do we have? Single cell bacteria can reproduce itself every 20 minutes. So after 20 minutes, we'll have 2, and then 4, and then 8, and then 16, 32, 64, 128, 256, and 512. What does that look like graphically? Well, let's see. If I put that on a graph, we need a lot of room on the y-axis because it goes from 1 all the way up to 512 in pretty fast steps, right? What you often see is when people do problems like this is that, that's t0, and they'll just use intervals. So this is actually, you can think of this as a 1. This is what value you get after your first interval of 20, and then your second, then your third, then your fourth, fifth, sixth, seventh, 8 and 9 intervals. Either way, on the y-axis I need to go from 1 to 512. So if that's like 500, then half of that would be like 250, right? So that's 250. So I'm going to say that's 100, that's 200, 250, 300, 400, and 500. So can we graph this? Well, at 0 we're at 1, so that's right there on the x-axis. And then after 20 minutes we're at 2, so we're still on the x-axis pretty much. And then 40, we're at 4, still there, so 20, 40, 60, we're at 8, still on there, at 80, we're at 16, we're basically still on there, because keep in mind that that's 100, so where were we? So that's 0, 1, 2, 3, 4, we're in the 5th interval, so we're at 32, and we're finally coming off the x-axis a little bit, 32, 64, just past halfway, 128, we're over here, 256, about 250, and then all the way up to just over 500. And so an exponential function looks like this. It increases very rapidly once it really starts to increase, and then it approaches the x-axis. So this is actually an asymptote, the x-axis. So this was time. We'll call this intervals of 20 minutes. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 100, 200, 250, 3, 400, 500 the number of bacteria. Okay. Alright, I should model good habits, so I wanted to make sure I put some labels on this. Okay? So that's what an exponential function looks like. It sharply increasing, it stays above the x-axis, it doesn't drop below, so asymptotes and no negative values, at least not if you have a positive starting initial value. Okay? If you have to check if something is an exponential function, then one way that you can do that is you can take consecutive numbers. Well, where am I getting consecutive from here? So if I think of x as my first value, so if I say x is 4, and then x plus 1 would be 5, so you take consecutive x's and you divide them out. And if you get a constant, then we know we're dealing with an exponential function. Okay, so that's an easy check that we can do. Determine whether a given function is linear, exponential, neither. So here's the check. So how do you get from 5 to 2? Well, you can multiply or divide, I say, but let's look for subtracting first. So 2 minus 1, negative 3, negative 1 minus 3, negative 4, negative 3. So we're always subtracting 3. That's called our constant rate of change. Also abbreviated often by the word slope. So that's a linear function. For those that are exponential, find an exponential function. Oh, let's find the linear one here. Okay, well, that constant rate of change, or slope, so I should be able to write y equals negative 3x plus, and then right there is the y-intercept, and so that's done. Right, what about this? So 2 to 4 is plus 2, from 4 to 7 is plus 3, plus 4, plus 5. Definitely a pattern, but not a linear pattern. It's also not a multiplying pattern, because 2 times 2 is 4, but 4 times 2 is 7. Here's something neat that's not in here. This is actually a quadratic pattern, because if you look at the first change, so the first change is not constant, but 3 to 4 is also plus 1, from 4 to 5 is also plus 1. So this is called like your second iteration. So the change in the second iteration is constant, so because of that, this is a quadratic function. And then we could find out what it is in this case if you wanted to work a system and then just plug in values for x and y, and you could write an equation for this fairly quickly, because 0, 4 is there, so if you use 0 you should get 4, so you know c is 4. You can use that to find the other ones fairly quickly. Okay, so this is probably our exponential function. So let's see, 32 to 16 is minus 16, 16 is minus 8, it's minus 4. So it's not a constant rate of change, but you can sort of see here that we're always halving this. And then, so what you then need to do is, well, let's check then for the whole division thing. So what do you get when you take consecutive values? So if you, and keep in mind that you need to take the larger x divided by the smaller x. So what is 16 divided by 32? Well, that's a half. And 16, and for example here, then it would be 8 divided by 16, which is also a half. And 2 divided by 4. I skipped 8, or 4 divided by 8, because I ran out of room a little bit. So that's called a constant ratio, right? So if we have a constant ratio, then we know it's exponential, and then this is actually the base. So right now, I know that I have c, and I have a base of a half, and then I have an x. This is your initial value, because it occurs at t of 0, if we think of this as time. You can literally solve for this. You can write 16 equals a half to the power of 0, which is 1. So you can get 16 out of that way as well. So the actual function here would be y equals 16 and then a half to the power of x. Okay? Okay, moving on. Graph the following two functions. 2 times 3 to the x. You can just make a table for it, as far as I'm concerned. If you know, what an exponential looks like, you can do this with transformations, but you can just plug in some values, and see what happens. So 0 is easy. You should get 2 times 3 to the power of 0, which is just 2. Here we get 3 to the first, which is 3, so that's 6. And then here we get 3 squared, which is 9 times 2 is 18. And then the negative exponents give us fractions, right? So that's 2 over 3. And then if you make that a negative 2, you should get 2 over 9. You could also realize that we just, to go from 2 to 6, you're multiplying by 3. So the other way around would be dividing. Okay. So what does that look like? I'm getting small values over here, right? So on the y side, on the negative side for x, I'm getting some rather small values, so that means that it's approaching the asymptote on that side. And then at 0, I'm at 2. At 1, I'm at 6. So 1, 2, 3, 4, 5, 6. And I can't even do 2 anymore. I can do negative 1 2/3, so if that's 1 2/3 is about here, 2 over 9 would be here. And then that's a pretty good picture. If I can get it to come out. Okay. Try not to make it that bad over here, but try really hard not to cross the x-axis, because this is an asymptote, right? Okay, how about a half to the power of x? Well, so what does that half do? So at 0, we're still getting a half to the power of 0 is 1. At 1, a half to the power of, well, that's your half. So this looks like this flipped, didn't it? Doesn't it? So a half squared is 1 over 4. Now I'm getting the small values on the positive axis. So there used to be over here. So these were the fractions. And now here, I should get my larger values on this side. So the negative exponent means you flip it. So that becomes 2 over 1, which is 2. So we are getting bigger values over here. So a half to the negative second, so that would be a 2 squared, which you can flip that, so that is 4. Okay, so graphing that then, sorry. And we're still not going to cross the x-axis, so but this one won't run this way anymore, it's going to run this way. So at 0 we were at 1, at 1 we're at a half, at 2 we're at a quarter, negative 1 we're at 2, at negative 2 we're at 4, and that should give me enough. And again, horizontal asymptote at y equals 0. Okay. So here are some properties. So if a is larger than 1, so if the base is a positive, then we have an increasing function. It should go through 0, 1, and then the coordinates here at a negative 1 would be 1 over a, because you flip the fraction, and at 1 you will get a. If a is between 0 and 1, so if it is a fraction, then we have a decreasing function. Still share 0, 1, but now 1 over a is what you get over here. Keep in mind that a here is a fraction, so 1 over a would be 1 divided by a half, so that is a 2. And then here we get our smaller values. Okay? Now I do want to show sort of the connection here between negative exponents and what's going on here as well. So a more common way to write this function, at least in word problem, is that a half is often written as 2 to the negative 1. And so the reason people do this is because you could write that as 2 to the negative x. And it's a little easier to see that it is a decreasing function. So if this is a negative exponent, decreasing function. If it's a positive exponent, then we have an increasing function. Please keep in mind that negative exponents have absolutely nothing to do with negative numbers. Okay? Nothing. Negative exponents means that you have a fraction. We don't have negative values, at least not out of the function right now. Okay, let's see, last one. So we're going to graph that function. Let me get rid of this homework thing over here. Graph it, and then I guess I can't do it because it's on the other layer. And then determine the domain, the range, and the horizontal asymptote. Okay, I guess I didn't go over all of these things very well, did I? They're smooth and continuous, both of them. This one is completely increasing, this one's fully decreasing. And I think that's it. And both functions are one-to-one, so they should have an inverse. Okay. So what do you do here? Well, you could make a table. And in this case, what you're actually interested in is you want to know when x plus 1 is equal to 0. So the reason we're doing that is because that seems to be sort of the anchor of both of these graphs, right? 0, you get 1. At 0, you get 1. Well, that would be if it's an a to the x. Okay. But if it's an a to the x plus 1, then 0 occurs at a negative 1. So the reason I did that is because that's sort of the middle of my table. So I want a negative 1 sort of in the middle. Because now I get 2 times 3 to the power of 0, which is 1. So 2 times 1 is 2, minus 4, that's a negative 2. And then I should pick some values that are larger than that. So 0. At 0 you would have 1. 0 plus 1 is 1, right? Minus 4, so 3 times 2 is 6, minus 4 is 2. And then at 1 you would get a 3 squared, which is 9 times 2 is 18, minus 4 is 14. And then here we should be getting smaller numbers. So we get a negative 1 there, minus 4. So that is 2/3 minus 4, which is a negative 3 1/3. And then negative 3, 2 to the power of negative 2 minus 4. So 3, that's 2 over 9 minus 4. So 2 over 9 minus 4. That would be a negative 3 7 over 9. So what is the horizontal asymptote over here? Okay, so if I may pick a super big negative over here, then this becomes a 2 over a very big number, so basically that becomes 0. So the negative 4, so the negative 4, y equals a negative 4, is your horizontal asymptote. Okay, you won't quite get there. But if we pick a very large negative x, then the function will almost be a negative 4. Okay. How about the domain and the range? Well, we should be able to figure that out based on the graph, right? So here's another way that you can look at horizontal asymptote. If you look at this as a negative 4, well, I mean, it is a negative 4. What I meant to say is if you look at the negative 4, that's a shift down of 4 units. So what used to be the x, the horizontal asymptote would be here. That was shifted down 1, 2, 3, 4 units. So our new x-axis, based on that shift, is over here. If the horizontal asymptote is not at the x-axis, it's custom to graph it. You don't always have to put what it is with it, but I'd like to be thorough on this one. So what do we get? -3. So -3, I am almost there. I'm at a -2. I'm at a -3 1/3. I'm at a -1. I'm at a -2. At 0. We're at 2. I'm at 1. I'm at 14. I can't even really graph that. So here is a reasonable picture of that exponential function. So what did we do? We got the horizontal asymptote taken care of. The domain, well, you can plug in any x that you want, right? So the domain will be all real numbers. And then the range, we have a horizontal asymptote, so we don't quite get to a -4, but we will get to any positive value that we want. And actually we get there rather quickly, and that's one of the things that exponential functions do. Okay, thank you.